This is chapter 12.1 continued. We are going to continue to talk about limits. I'm going to show you some algebraic and graphic ways of evaluating limits. I have my materials ready. I have my graphing calculator out. We went over some different properties of limits, some more theoretical properties of limits, and what we're going to do today is we're going to kind of show you how that works when the pavement, when the rubber hits the road. So how do I actually do this? Theoretically speaking, remember we're looking for this. Anytime we get weird where they don't come together, we don't have a limit. If we have things that come together, we have a limit. We don't care exactly what happens at that specific spot. We care what happens really, really close to the spot. So I have some properties here, some different problems that I'm going to talk about. These are very basic properties of limits. I'm going to go kind of fast. If you need to pause the video, feel free to pause the video. So the first one, the first property is the constant property. What happens when there is no x value and you're trying to evaluate a limit? For instance, we're going to find the limit as x goes to 5 of some constant, let's say like it's 4. And the rule is the limit at a constant is the value of the constant. So the constant is 4, and so my answer is 4. And let's think about this graphically. 1, 2, 3, 4. This is the equation, y equals 4. And if I did y equals 4, I would have that picture. And then this one's the limit as x goes to 5. So I'd go out to 1, 2, 3, 4, 5. And I ask myself, at 5, does the graph come together? And I'll just put a little dot here at 5. And I ask myself, from the left and from the right, yes, it comes together right there. They come together around that spot. And the value, it comes together. So if I go over to 5, I go up to the graph. They come together. And I'll go over to the y-axis, and my value is 4. And it makes sense that it's 4. Now, so that's the graphical approach. Direct substitution it basically says, as we go through this, what would be the value I would get if I would take this value here, the limit as x goes to 5, if I would take that 5 value and directly plug it into the equation? Well, there is no place to plug it into the equation. So direct substitution for the limit as x goes to 5 says directly plug the 5 in. What do I get out? Well, I still get out a 4. So the limit of a constant is the value of the constant. That is a limit rule. All right, number 2, the identity function. So we had the constant function. That's one we talk about. The next one, we've seen this one before, the identity. So the limit as x goes to -2 of x, and y equals x is the identity function. Well, let's think about it from a graphical standpoint. Y equals x looks like this. We've seen that many times. I want to know what the value is at -2. So if I go to -2 and I go to my graph, I'm right here, and I ask myself, as we get closer to that point, do those two ends come together? Well, yes, they do. So I go over to 2, I go down to the graph, I go over, and my value is 2. The limit as x goes to -2 is -2. And you notice, again, we're going to directly substitute the value in. So we're going to go with the limit as x goes to -2 of x says, what value would you get if you plugged -2 directly in for x? You would get -2. Direct substitution is great. We can plug the number in. We wouldn't even necessarily need a graph. Okay? The next one is some like power function. Let's call it some power function. The limit as x goes to, let's just send it to 2 of x cubed. And here we are in my favorite one. We got the Johnny T looking graph like that. It goes up. So we have this graph that starts down here and it goes up. And we're asking ourselves, what's happening at 2? So I'll go over to 2, I'll go up to the graph, and I'll put a little dot there. And I'm asking myself, at that dot, do those values come together? Well, yes, they do. And what is the value? I didn't mark this axis because, well, if I plug a 2 in, I'll get 8. So if I go over to 2 and I go over to the graph, I get a value of 8. So I find the limit as x goes to 2 of x cubed, in this case, is 8. And that's what I would get if I applied direct substitution. The limit as x goes to 2 of x cubed asks me, hey, what would I get using direct substitution if I took the 2 and I plugged it directly in? I'll get 2 cubed, which is 8. And in both cases, I got 8. And then the last one I'll go over is just the square root function. A square root limit. So I'm going to have the limit as x goes to, I don't know, some value. Let's send x to 4 of the square root of x. Now, the first thing about this, whenever you do a square root one, you have to understand there's something limiting here. So if you think about what the picture looks like, it's this picture. And I can't actually find the limit back here because there is no graph. I have no values coming together. So the caveat on this is this value, which sometimes they'll call c, this c value, that c value has to be greater than or equal to 0 in order to find limits on the square root function. But let's find the square root function. Let's go to 4. 1, 2, 3, 4, and we'll find the limit as I go to 4. So I go up to my graph. Do they come together? Yes, they do. And they come together at 2. So the limit of this, the limit as x goes to 4 on this graph is 2. And that is what I would get if I plugged the limit as x goes to 4 of the square root of x. That's what I would get if I directly substituted it in. I would get a 2 value. So sometimes, and there's a lot of times that we do these, you can actually find the limit by taking the number that is in this little spot right here and directly plugging it into the equation, and out will fall your answer. And that's kind of nice. There are some places that doesn't work, and we'll continue to talk about this, but for right now, direct substitution is great when we can use it. Okay, a couple more properties, and I'm going to go very quickly through these because they are kind of what I would expect. The first one is a scalar property. And the scalar property simply says this. If I have the limit as x goes to 5 of 5x cubed, you can take that scalar, you can pull it out in front, and you can shove the 5 in. 5 times the limit as x goes to 5 of x cubed says I can take the 5, I can plug it right in for that. Well, let me think. That would be, I would get 125 is 5 cubed, so I'd take 5 times 125, which is 625. You can pull a scalar out in front if you need to. An adding and subtracting property says you can divide limits up if you need to. So we can find the limit as x goes to 2 of x squared plus x. So I can find both of these limits individually. I can find the limit as x goes to 2 of x squared, and I can add to it the limit as x goes to 2 of x. Well, I plug a 2 in there, I get 4, plus I plug a 2 in there, I get 2. 4 plus 2 is 6. So I can divide limits up like that. The next one is a multiply and divide property. Multiply and divide property. You can actually take limits and you can divide them up. I can find the limit as x goes to 9 of x radical x. What I can do with that is I can find the limit as x goes to 9 of x and multiply it by the limit as x goes to 9 of radical x. And again, on all these, I'm just using direct substitution, which means I'm just taking the number and I'm plugging it in. So it's 9 times 3. Square root of 9 is 3. 9 times 3 is 27. And I can divide those up and I can find them individually. And then the last one is called the power rule. Power rule. And for the power rule, I can take the limit as x goes to 2 of x to the 4th. I can take the 2 and I can shove it in, limit as x goes to 2 of x, and then I can apply the power later. So I can take the 2 and I can plug it in. I get 2. 2 to the 4th is 2 times 2 is 4 times 2 is 8 times 2 is 16. These properties exist. Don't use them a ton. A lot of times what we want to do is we want to just plug the number in originally and we don't have to break it apart. But these properties, what they allow you to do is they allow you to break limits apart when you need to. I might refer to these a little bit. We'll use them from time to time, but we'll go from there. So we're going to have a little blast from the past right now, okay? And we're going to do some limits of a tangent function. And the first thing I want you to do is sine is y, cosine is x, tangent is y over x. Sine is y, cosine is x, tangent is y over x. Sine is y, cosine is x, tangent is y over x. And what we would like to be able to do is we'd like to be able to use direct substitution for this. So what I'm going to start with, let's just see, I'm going to find the limit as x goes to 3 pi over 4. Do you remember where 3 pi over 4 is? 1 pi over 4, 2 pi over 4. Wait. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. 3 pi over 4 was right there. That ordered pair. That ordered pair was negative radical 2 over 2, radical 2 over 2. The tangent at 3 pi over 4. The tangent at 3 pi over 4. What was that value? So y over x. Tangent is y value over the x value. It's negative 1. So as I go through these, I'm gonna use that idea to try to evaluate some of these. So here we go. So I'm going to find the limit as x goes to 3 pi over 4 of x over tangent of x. And I'm going to do this with direct substitution. So I'm going to take 3 pi over 4 and plug it in all over the tangent of 3 pi over 4. Well, 3 pi over 4 is 3 pi over 4. And I know the tangent at 3 pi over 4 is negative 1. And I get 3 pi over 4 over negative 1, which is negative 3 pi over 4. So I got the first answer with direct substitution. It worked great. I plugged it in and we went. Let's try the next one. Find the limit as x goes to pi of x over tan x. So my x value is pi. And I'll put tangent of pi. Well, I got pi on top. And then the tangent at pi, well, pi is over here. And that ordered pair is left 1, up and down 0. Left 1, negative 0. So the tangent at pi is, well, it's the y value over the x value. Y over x. 0 over negative 1 is 0. So I get pi over 0, which gives me undefined. Direct substitution, plugging a number directly in, gave me an undefined value. That's interesting. Let's see if I can get a little bit more here. 2 more. The limit as x goes to 0. So I'll plug zeros in. 0 over the tangent of 0. Tangent of 0. Let's go over here. Here's 0 right here. That order pair is 1 comma 0. Tangent is y over x. The tangent at 0, just 0, is y over x, which is 0. So I get tangent at 0 is 0 over 0. That's also undefined. One more. Tangent 3 pi over 2. So I'm going to plug 3 pi over 2 in, all over the tangent at 3 pi over 2. All right, let's find 3 pi over 2. 1 pi over 2, 2 pi over 2. 3 pi over 2 is right here, and that ordered pair is 0, negative 1. Y over x is undefined, so I get 3 pi over 2 over undefined. Which, what is something over undefined? I would probably call it undefined. Now, there's actually a lot going on here with the theory behind limits. I just used direct substitution, which means I took the value, I plugged it directly in for the x's, and I evaluated. That's like the brute force way. The theory way is we don't really care what happens at that spot anyway. So the fact that I plugged a 0 in here, 0 there, and I got 0 over 0, and I got undefined, that's specifically at that point. At 0, I get a value that doesn't even exist. There might be a hole there, there might be an asymptote there might be a lot going on there. But it doesn't necessarily mean that the limit doesn't exist at that point, because maybe I get one of these guys and they're coming together and there's a little mini hole there, and at the point itself it's undefined, but on each side they're approaching some value that we're going to find. So what I did was I went on Desmos and I plugged this in. So what I'd like you to do is I'd like you to hit pause or get your phone out, whatever, and on Desmos, and I want you to plug in x over tan x, and I'm gonna write my values here. It was 3 pi over 4, 3 pi over 4. It was at pi. It was at 0, and it was at 3 pi over 2. I don't know if you can see those. Oh, right there. Okay, and I'm going to go to Desmos because I want to see what's going on the graph here. So I got this crazy thing here, okay, when I plug this graph in. And that's not a graph we would do by hand. We just got that crazy thing. And what we want to do is we want to know what happens really close. Maybe there's holes in this graph that we just don't know about. So let's go in and let's evaluate what's going on like at each specific point. So I got 3 pi over 4. 3 pi over 4, well, I'm going to decimalize that. 3 pi over 4. And I got 2.35. So I got like 2.35 right here. 2.35 is about right here. And I can go down to my graph, and I can get a value. Now, I want to go back here real quick. Let's see, what did we get at 3 pi over 4? At 3 pi over 4, we got negative 3 pi over 4. That was what our answer was. So what we're saying here is at 3 pi over 4, which is that 2 point whatever, I should be able to go down 2 point whatever, and I'll go over to the axes, and that ordered pair right there on the graph, that would be the ordered pair 3 pi over 4, negative 3 pi over 4. And more importantly, at that point, you get this convergence, this value where you could come together. They come together. So the limit here is 3 pi over 4. I followed that. That was good. Now the limit at 0. Now the limit at 0 we found to be undefined. But I go to my graph. At 0, I go up to my graph, and I notice these two ends of the graph are coming together. There must be a hole at 0. In fact, if I zoomed in far enough, I bet there's a little hole where it was dun 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 dun. Hey, I'm okay. I'm Mr. Big Man. But oh no, little skinny queen. Oh no! Whoosh, falls right through. It's really microscopic, but it's there. But they come together. So on each side of that hole, what happens is, I got this little hole here. I do have a value, and notice it's coming up here, and it's coming, and it's approaching this value. It's approaching 1 from both sides. So this answer is 1. It's not undefined, which is really weird. All right. Oh wait, this answer is 1. That answer is 1. Okay, let's go to pi. I skipped pi accidentally. So pi is about 3.14, 3.14 right there. And this is the first one where you get some values. Now look, if I drew this in, I'd have a vertical asymptote right there at 3.14. And I'm coming in here from the left side, and I'm coming in here from the right side, and I have this. I have these two values, and they're going like this, and they're diverging from each other, and they're not converging around a point. Well, anytime that happens, the limit does not exist. So we were right when we put does not exist for pi. And let's go to 3 pi over 2. I need to find that decimal. 3 pi over 2. And I got 4.71. 4.71 is right about 1, 2, 3, 4.71 is right about here. And we got undefined for 4.71 also. But I noticed on my graph, as these two, as I approach the graph from the left, and I approach the graph, approach the point from the left and then the right. Yeah, we got all these weirdness. But then as I get really, really close to this value right here, it converges around that spot. And that spot on that graph, if I go over into the graph, that spot is 0. So, bottom line, we tried direct substitution. We got some undefined values. And when you get undefined values through direct substitution, it doesn't necessarily mean that there's not a limit. It just means at that specific spot, there is no value. We care what happens really, really close to the spot. Are those values approaching each other as we get microscopically close to the spot? Even though there might be a hole there, that's okay. All right, we got one more thing here today on limits. In your book, there's page 859. You may or may not have access to that online. If you want to go there and read that, you can. But I'm going to give you the gist of it. Okay? 4 polynomials. Here it is, 4 polynomials. And we ask ourselves, what's a polynomial? Well, a polynomial is all of that fun dance party stuff that we did. 5x cubed minus 3x squared plus 2x minus 4. They went like this. It was x to the 4th with a negative leading coefficient. It was like this. Okay, and we had all these different pictures, and we got jiggy with it, and we did all that fun stuff back when we had class. Now we have a polynomial, and a polynomial is any of those types. So I'm going to give you one. So for polynomials, I'm going to put such as, and the one I have here is y equals x to the 4th, plus 2x cubed minus x plus 2x cubed minus x plus 1. For polynomials such as that, the rule is direct substitution always works. Direct substitution always works. And what that means is if I have a number and it asks me for the limit as x goes to 2 or 4 or whatever that number, I can take that number and I can plug it in right into the graph, or into the equation, and I can find the value. Or I could set my table up so that the table shows the values that occur on each side of the point. But direct substitution is a really good way. So we want to be able to take a number and plug it in. So for instance, if I was going to find the limit as x goes to 3 of this polynomial function, and I'm going to recopy it, of x to the 4th plus 2x cubed minus x plus 1. What we're saying here is we can take that number and we can just shove it directly in. So I take 3 to the 4th plus 2 times 3 cubed minus 3 plus 1. And notice I just took the 3 right there and I plugged it in. 3 to the 4th is 81 plus 27 times 2 is 14, 54. 54 minus 3 plus 1. So I'm even going to grab my calculator. 81 plus 54 minus 3 plus 1 is 133. We got 133. That's the limit as x goes to 3 of that polynomial function. And we could find the limit at any spot on the polynomial function. And that kind of goes to the reason why it always works. Polynomial functions, they're continuous. There's no holes, gaps, breaks, whatever. So this picture right here would be this. And we can take that number and we can plug it in. And we just found at 3 the answer of this. I mean, if I went to 3 on the graph, I'd have to go all the way up to 133 on the graph to find out the point. It'd be a big, huge W shape, something or other. But for non-polynomial functions, for polynomials, for non-polynomial functions, and you saw one like that with the tangent graph. It was x over tangent x. That's not a polynomial function. Direct substitution may or may not work. We don't know. You can try to plug in a number, but if you get some funky undefined values, you might have to go back and do something else. You might have to set it up on a graphing calculator. You might have to plug in Desmos and then look at the graph and ask yourself, are you getting one of these convergence, or are you getting something where it gets funky? Okay, any of those cases would be ones where it doesn't exist. So here is a common one, and it's a rational function. The limit as x goes to -1. I have a couple. The limit as x goes to -1. I think I have -1. Yep, of x squared plus x minus 6. X squared plus x minus 6, all over x plus 3. And then we're going to do the limit as x goes to 1. The limit as x goes to 1 of x squared minus 1. X squared minus 1 over x minus 1. And then we're going to do the limit as x goes to 2. The limit as x goes to 2 of x cubed minus 2x squared minus x plus 2 all over x squared minus 3x plus 2. Okay, now I have 3 rational functions here, and sometimes I'll be able to take the number and I'll be able to plug it right in, and sometimes it doesn't work. So we try direct substitution because direct substitution is great. I take the -1, I plug it in, and we'll go from there. So I'm gonna take that value and plug it in. -1 squared plus -1 minus 6 all over -1 plus 3. That's 1 minus 1 minus 6. 1 minus 1 minus 6 is -6 all over -1 plus 3, which is 2. I got -3 out of that when I plugged it directly in. So there's a case where, hey, direct substitution was great. We could plug it in and we got the answer. Let's try plugging in 1 on this graph. So I take 1 squared minus 1 all over 1 minus 1. I get 1 minus 1 is 0 over 0. And I get this undefined value at the point itself. That does not mean that the limit does not exist. So stick with me now, okay? We're almost done. We're getting there. I want you to go to your graphing calculator, and I want you to plug that in. X squared minus 1 over x minus 1. X squared minus, oops, I'm going to use alpha F1. X squared minus 1 all over x minus 1. And I'm going to graph it. And when I do that, I get a straight line, which is interesting. It's a rational expression. By the way, you get a straight line because there's an x squared up here and the x down there. So theoretically, this x cancels out that x, and you only have one x on the top. You only have one x on the top. It's a straight line. But what I'm caring about is what's happening at 1. Okay? From a graphical standpoint, this graph looks like this. And I care what happens at 1. So I go over to 1, I go up to my graph, and I go over to the y-axis, and I ask myself, how high up am I? And I can do that with my cursor. I'm going to take my cursor, I'm going to go over to 1, I'm going to go up to the graph, and if I go over to 1 and I go up to the graph, I'm about at 2, and you could zoom in and see that. So it looks like the answer here, just from a graphical perspective, from the graph, is equal to 2. You could also get this by your table, and we did this last week, so I want to practice it again. So I'm going to go second table set. I'm going to start my table this time at that limit value of 1. So my table start will be 1, and I'm going to change my table by 0.001. And the keys I hit second, that table set button. So I started at 1 and I changed it by 0.001, and now I'm going to go to my table. And to get to the table, you hit second table and it will go to your table. I cursor up a little bit here. I notice at 1 it says error. It says error here when I plug in the 1, which it should. Our algebra showed us that it was an error. But I care what happens on each side of the 2, on each side of the 1. And on each side of the 1, I notice those numbers, well, they're getting closer and closer to, look at that blue number. That's really close to 2. And that blue number down there, that's really close to 2. So from a table standpoint, I also get 2. And the last problem. So direct substitution, again, direct substitution didn't work here. But then I went to my graph and I went to my table and I found out that the limit does exist. And the last one, direct substitution. I bet it doesn't work. I'm just going to plug in a 2. I got on the bottom. Watch what happens, just because I kind of know what's coming. So I plug in a 2 here. I got 4 minus 2 times 3 is 6. 4 minus 6 plus 2, I get 0 on the bottom of the fraction. It's a rational expression. Direct substitution doesn't work. So I'm going to go back to my y equals, and I'm going to plug into that screen. I'm going to plug this in, and it is kind of long, but that's okay. X to the third minus 2x. Oops, I'm going to clear that out. Alpha f1 x to the third minus 2x squared. 2x squared minus x plus 2 all over x squared minus 3x plus 2. And I'm going to go right to my table. I'm going to set my table up because I want to see what's going on at my table. So I'm going to go to table set, and I'm going to start my table at this value. Start my table at the 2. And I'm still going to change it by 0.001. And I'll go to my table. And when we plug 2 in, we notice that we had 0 on the bottom of the fraction, which shows up as error on your calculator. But I notice on each side of 2, well, on one side of 2, I got 2.999, and the other side of 2, I got 3.001. This is approaching 3. So I got a value of 3 for the limit. Wow, a lot of theoretical stuff. We will do some of your homework together coming in our next time, our next class period here. We will do some of this together. I know this is a lot of theory and it's weird, But it's awesome stuff. So looking forward to our next meeting. Have a great day.